Hello, my name is Etienne Robein. I'm a freelance consultant in geophysics. My main activity after a career with major oil companies is to deliver courses and training sessions on the seismic method, and especially on seismic processing and time and depth imaging technology. In this frame, by the way, I published 2 textbooks with EAGE publications on velocity and reflection seismics and seismic imaging. The title of my lecture today is Reverse Time Migration. How does it work? How to use it? Building an accurate image of the subsurface in complex geological settings remains a serious issue for geophysicists. If the first challenge in this context remains to build a model of the velocity at which waves propagate in the subsurface, the second one is to compute the seismic image itself, and reverse time migrations, or RTM, is one answer to this challenge. In this presentation, I will explain how RTM works and why it provides generally superior results to those of other migration methods in complex areas. Unfortunately, at a cost, RTM is a computer-intensive tool. The lecture is organized as follows. Firstly, I remind the concepts of down and upgoing wavefield and reflection coefficient. Secondly, I use these concepts to explain how RTM works with the help of a synthetic example. Thirdly, I discuss 2 issues of the methods, noise and computing cost, to conclude with the benefits and limitations of RTM compared with ray-based and Y-wave methods. So let's start with the Wavefield movie. In the seismic experiments, we generate a disturbance at the surface that propagates into the Earth. I call Wavefield movie the history of that disturbance in the subsurface, expressed as pressure variations or particle vibrations for the duration of a short recording. For seismic imaging purposes, geophysicists have developed methods and tools to emulate the real Wavefield movie in a velocity model assumed to represent the propagation velocity in the subsurface. This forward modeling exercise is a fundamental element of RTM, so let's do it using a simple 2D example. Here is the color-coded 2D anisotropic velocity model which I will use for my demo. Velocity models for RTMs are gridded objects, just like seismic images and wavefronts. In order not to forget that RTM is used in complex geological settings, I show here an example of such a real 3D velocity model, courtesy of Schlumberger-Olga-Straveva. The zoom here reminds us that the grid size is an important parameter. It must be adapted to include details in the velocity model and avoid unstable numerical schemes. Let's compute now the wavelet movie itself, starting with the first snapshot. By the way, a snapshot at the time t of the movie represents the pressure field in the subsurface at that specific time. Snapshot n is computing recursively from previous snapshots by numerically solving the acoustic wave equation at each step. We call Wavefield extrapolation in time, or WE, this computation snapshot by snapshot of the movie. This technique used in RTM honors the physical law of propagation, and this explains why RTM is accurate and robust in complex models. And the recursion goes on as long as necessary. To emulate the source, we numerically impose the wavefield to be equal to the signature amplitude at each time step at the shot location. This is a surface boundary condition. Here I take a zero-phase signal, as it's often the case in real life. At the same time, we can capture the wavefield at the streamer location, emulating in this way the actual shot recording. Let's the movie develop and the wavefield expand, and we stop it at 140 milliseconds. At that moment, the wavefield hits a reflector in the shape of a change in velocity and density, and these generate a reflection, and part of the wavefield starts to propagate upwards. Let's look at the wavefield 20 milliseconds later. We classically split the whole wavefield and distinguish the downgoing wavefield, which is the pressure disturbance directly generated by the source, highlighted in red, and the upgoing wavefield, the pressure disturbance generated at the reflector. The phenomenon of reflections can be quantified by the reflection coefficient of the reflector, let's call it R. By definition, the amplitude of the upgoing wavefield at the reflector is R times the amplitude of the impinging downgoing wave field. The reflection coefficient is an important feature of today's discussion, since precisely the seismic image we are looking for is supposed to be a representation of the reflection coefficient in the Earth, as illustrated here with the result of RTM. Let's the movie go on again. And so on, until maximum time 1.5 seconds in my example. So, we have so far firstly reviewed the phenomenon of reflection, secondly briefly presented the time-step Wavefield extrapolation method. Let's see now how we use this to migrate a shot gather. We mean by migration to transform a shot into an image of the reflection coefficient in depth. This is what RTM does, but how? For that, let us come back to a snapshot, say 660 milliseconds as an example. I highlighted in red and in blue the down and upgoing wave fields respectively. Imagine now that we can reconstruct separately the down and upgoing wave fields at each time, here 660. The trick of RTM is that we can deduce from these two fields if there are reflectors and where they are. How do we do it? To answer this question, we call the famous imaging principle stated by Professor Claerbout back in the early 70s. Reflectors exist at points in the ground where the first arrival of a downgoing wave is time coincident with an upgoing wave. The two wave fields in blue and red are time coincident. If we superimpose them, we can compare them and visually detect where the two fields are also space coincident. I highlight these coincidences with yellow bubbles. According to the imaging principles, this is where the reflectors are. But we can tell more. From the definition of the reflection coefficient R, we can also estimate its relative value, simply dividing the blue field by the red field. Well, at least theoretically. Lots of issues here, theoretical and practical. But I'm not going into these, and to make a long story short, we have a way to get an image of reflection coefficient in depth, at least for the reflectors elements which were illuminated at that moment in the subsurface. Note that if an element of reflector is illuminated, it is for the duration of the passing of the downgoing wave field. And second, that of course other elements of reflectors will be illuminated at other times as the downgoing wave fields propagate. So it makes sense to repeat the process for every single time and accumulate the results to get the reflectors coefficients everywhere. And of course, don't forget that the image of R is precisely the seismic image we are looking for. Well, I have no time to discuss amplitudes, phase, illuminations, just to name a few of many issues here. Basically, from this discussion on the imaging principle, I do have my RTM workflow. First of all, each shot is processed separately. Now, for each shot, we compute the downgoing wave field, we reconstruct the upgoing wave field, and perform some kind of comparisons at each snapshot time to get the contribution of that time to the final image. And finally, we accumulate the results over time to get one migrated shot. Then we repeat for all shots and stack the results together. Okay, so the inputs to RTM are the velocity model, the shot gather with some pre-processing applied to it, and its acquisition layout. Next, we define the volume around the shot in which we are going to migrate. I call it the migration aperture. For efficiency reasons, it doesn't need to be the full survey volume. Its choice is a trade-off between efficiency and risk to lose information. The first job is to get the downgoing wave field. For that, we simply compute the full wave field movie as shown in part 1. We know that it includes the upgoing wave fields, but we simply ignore it based on the fact that it is R times lower in amplitude, the reflection coefficient R being small, a few percent in general. An important point is that we need to store everything, every single snapshot. The issue is that snapshots are large 3D volume, the size of the aperture, and we compute and store classically one such a volume every millisecond. I'll give some figures about that in a moment. The next job is to reconstruct the full history of the upgoing wave field, and this is not so intuitive. So it's reverse time. Let's reverse the time. Okay. Now, we saw earlier that at any time, what is recorded in the shot gather is the upgoing wave field amplitude at the surface along the streamer at that time. So the idea is to impose this pressure by the amplitude of the shot at that time as a boundary condition for the upgoing wave field computation. And just like we computed the downgoing wave field movie with the source signature as a boundary condition, now we integrate the wave equations with the shot gather amplitude and the new boundary condition, just telling the equation that we extrapolate reverse time. We repeat the process every millisecond from the maximum recording time backwards and reconstruct in this way the upgoing wave field. So let's do it. Here it goes. You see the upgoing wave field being reconstructed as time goes on. I stop 1 second just to pinpoint as an example the upgoing elements of the reflection on reflector 3, 4, and 5. And you see on the right how the shot gather is feeding the backwards wave field extrapolation step by step like a spatial source. And so on until 0 time. So we have everything in place to run the RTM. We start again with the reconstruction of the upgoing wave field. Here it goes. Now that the upgoing wave field is well initialized, we may decide to start the actual RTM, say at 1 second. For that, we go and retrieve the corresponding downgoing wave field snapshot that we had computed and stored in the first job. Here it is. Next, we have to compare the blue and the red and check if there is a contribution to the image of reflection coefficient at that time. We saw earlier that we could theoretically achieve that by dividing the up blue by the down red. Obviously, this deconvolution, as we may call it, is not practical, as the down may vanish. So researchers came with more stable solutions, generally called imaging conditions. The most classical one is a so-called convolution, where the up blue is multiplied by the down red and scaled at the end by the downgoing energy. The simplest one is the correlation imaging condition, which I used here, where the up blue is simply multiplied by the down red. So the RTM process goes like that. Reconstruct the upgoing, retrieve the stored downgoing, multiplying one by the other to get the contribution of the snapshot time to the final migration. This is a green panel. And add this contribution to the seismic image progressively building up. In this way, the RTM image the black panel. We do that recursively every millisecond, although I display only every 20 milliseconds. So here it goes. Nothing had happened so far, but now we start to see something. The downgoing and upgoing are space coincident in the circles, and this creates a contribution to the image in green, which is added to the image in the making in black. Now we go on. Stop again at 6.6 seconds. We have superimposed the downgoing wavefront red curve onto the reconstructed upgoing wave field so that we see where they coincide. And once again, the green is the contribution of that time and the black is the RTM in the making. Keep on moving again. And now you see the deep horizons being imaged. And now we see the dipping and the shallow ones, and eventually job done. We have reverse time depth migrated the shot through the velocity model. How do we migrate the whole survey? Basically, all selected shots of the surveys are migrated separately. The final product is the sum of all migrated shots. There are ways to do the summation smartly in the sense that one avoids to add noise to good signals. So various techniques are commercially available for that, but not addressed here. So once this is one migrated shot, only what was illuminated by this shot can be imaged, and that would be the stack of 15 migrated shots. Okay, I discuss now two issues of RTM, noise and computing. You remember that when computing the downgoing wave field, we assume that the upgoing wave field genuinely regenerated was small in amplitudes compared to the downgoing wave. We have similar effect when we compute the upgoing wave field. We generate undesired downgoing wave fields on the right. The bad news is that these artifacts correlate, and the summation over time produces typical long wavelengths quasi-vertical noise. This is an example of the worst situations for noise generation, namely strong reflectors close to the surface, near the top of salt body. Various methods are implemented in practice to mitigate this effect, including filtering and sophisticated imaging conditions. However, the real issue and main limitation of RTM is the computing cost for high frequencies. The number of arithmetic operations to perform depends on the size of the 3D wave fields, which depend on the spatial sampling rate. The latter is constrained by the fact that the shortest wavelength in the data and its derivatives must be properly sampled to avoid numerical instabilities. This shortest wavelength, in turn, is a function of maximum frequency and minimum local velocity. At the end, the rule of thumb is that the number of operations increases with the force power of the maximum frequency in the data. And this is not good news. As an example, I take a typical migration aperture of 10 by 10 kilometers with 8 kilometers of depth. So for 20 Hz in a marine case, the size of the old snapshot of the downgoing wave field may be about 23 terabytes, and say n, big number, the number of arithmetic operations. If we want to go from 20 to 80 Hz, the storage is multiplied by more than 120, and the number of arithmetic operations is multiplied by 256, and this is a serious practical issue. Having explained now how RTM works and discussed its main limitation, it is time to present its benefits, firstly compared with ray-based methods, and secondly with the one-way WEM. A crucial advantage of wave field extrapolation based against ray-based method is their ability to handle complex models. By complex model, I mean models with short wavelengths of velocity changes. For ray-based methods such as Kirchhoff and beam migrations, let me make my point with this velocity model which, with a wiggly interface, a highly simplified representation of a complex top of salt. If you should raise in this model, as we would do for instance to compute a Kirchhoff migration operator, we will get this result. 3 rays with very close takeoff angles, and we get totally different ray paths. Almost impossible to compute a Kirchhoff migration operator. This is what I call a chaotic behavior. Wavefield extrapolation, on the contrary, if the grid size is adapted to the complexity of the model, will be stable. RTM works with this complex model. Here is a real case comparison courtesy of Ian Jones with Ion Geophysical. In this case, the complexity of the model comes from a gas leakage. Kirchhoff fails to image the reflectors below the gas cloud. RTM does a much better job. Another example now in the subsalt context from Andreoli et al. With ENI. Here the complexity is a salt canopy, and once again Kirchhoff fails because it uses ray tracing when wavefield extrapolation based RTM yields a much better result. Note, however, that the difference in vertical resolution in the sediments, high frequency were voluntarily not migrating RTM to save money and time at this stage of the project. RTM uses a two-way propagator. What's the difference with one-way propagators? So typical examples are diving or turning waves which may exist in a medium where velocity increases with depth. The downgoing wave is refracted up to the turning point where it starts to propagate backwards to the surface. Two ways, up and down. Ray-based migrations emulate these two types of two-way propagations, and RTM, which uses the wavefield extrapolation in time as we saw earlier, has no limitation either. Both allow us to image overhangs, provided they were eliminated during the survey. In the so-called wavefield extrapolation migration on WEM, we actually use one-way propagators in depth. They do not propagate waves beyond the turning points. Consequently, they cannot image overhangs and are deep limited. But they are much faster than RTM, with no practical frequency limitations. Okay, so another type of propagations are prism waves, also called multi-bounce waves. These are handled by RTM propagators, provided the various reflectors are correctly represented in the model. These propagations are more frequent than we initially thought and explain some good RTM results in complex geological structures. Here is a real case comparison courtesy of Ian Jones and Iron Geophysical, where you can see a salt flank imaged by the two-way RTM on the right and not visible on the one-way ROM on the left. Once again, the difference in vertical resolutions comes from the maximum frequency limited to 20 Hz for RTM for cost reasons. You may note also remnants of the typical RTM noise at the top of the salt on the right. And finally, a graph with no scale of relative computing effort of each method as a function of the maximum frequency. Ray-based Kirchhoff and fast beam migrations are independent of the frequency. Gaussian beam and WEM increase gently with frequency, the rule of thumb being that WEM at 80 Hz may require 10 times more computing power than Kirchhoff. And again, RTM increases with the force power of frequency. If it is comparable to other methods, say for 10 Hz or for 20 Hz, it would require 100 times more computing for 50 Hz and still unachievable figures for, say, broadband seismic at 100 Hz. So I come to my conclusions. RTM, because it uses an expensive but accurate solutions to the wave equation, is in theory the best migration tool commercially available today to address imaging problems in structurally complex geological settings. It's stable in complex models. It can migrate any dip, including overhangs. It handles turning and prism waves, addresses multipassing, and no other tools accumulate all these benefits. Its main limitations remain the computing cost to migrate frequencies higher than, say, 50 Hz. Although this limit is pushed up regularly with the new computers. RTM has been widely used so far, mainly in salt tectonics environment, but this is changing. Amplitude friendliness was not addressed in this short presentation, but in this domain and others, promising emergent technologies, including least squares RTM and the migration of multiples, are underway to lead to a more general use of RTM with big computers. Thank you for your attention. You can like and share this video and leave your comment down below. And for more e-lectures, take a look at the e-lecture playlist.